talking about probability. The sample space is everything that could happen. The sample space is every possible outcome that could happen, right? So if I say, what happens, what is the sample space for rolling 2 die? If I had 2 die, if I roll 2 die, what is the sample space? There it is in front of you. That's everything that could happen. I could get 2 ones. I could get a 2 and a 1. I could get a 3 and a 1. I can get a 4 and a 1. I could get a 5 and a 1, a 6 and a 1, and then a 1 and a 2, a 2 and a 2, a 3 and a 2, so on and so forth, right? There's 36 different things that can happen if I roll 2 die. Here's my question. I'm going to circle 2. This guy right here and this guy right there. Why are they both on there? Aren't they the same? I get this question a lot. People say those are the same. Why are they both? Why is it on there twice? Should they be on there twice or should they only be on there once?
Is it because there are 2 different types?
So what I want you to do right now, talk about it with the person closest to you. Okay? Are they the same? Are they different? Do they need to be on there twice? Is it necessary? Is it not necessary? Okay, go. Okay, so different, the same. Do they need to be on there twice? Is it just do I need to have both of those on there? Is it important? Because that's not the only one, right? A 1 and a 6, 6 and a 1, 2 and a 3, 3 and a 2, right? Is it necessary to have them both on there? Yeah, the answer is yes. You need to have both on there. Why?
Is it because are you like let's say if like the 2 and the 1 for the first one, we say that's true and the second one is false? Like, are we saying that the second dice doesn't like the 2 doesn't exist?
No, it's just saying you roll 2 die. The orange one is the first die. The bluish one is the second die. So if I roll 2 die, that could happen, or that could happen. But the question I get a lot is, those are the same thing, Mr. Flores. Why do I have to? Why are they on there twice? Why are they on there twice? It's
sequence matters.
There you go. What about the sequence is important? They're both a 3. What do you mean a higher chance?
And one of them 2 comes first and the other one comes second.
Yeah, why is that important? You're right. If one of them comes first, so a 2 comes first, right? And then a 1 comes second. Why is that important? You're right.
Sequence can denote different things.
Because the people who say it's the same thing are assuming that it's the sum, right? The sum is the same, but not the die. The dies aren't the same, right? Why? In that case, wouldn't we take out? I got a 2 and a 2. So when I took out a 3 and a 1 or a 1 and a 3, they both make the same, right? So just because they add up to be the same, because you're adding up the dots, doesn't mean it's the same event. They're different events. After the first dot, I had a 2. After the second dot, I had a 1. The roles were reversed here. If I only roll 1 die, those are different. They're different events. They happen in reverse order, but they're different events. So all of them need to be up there, even though some of them add up to be the same. Okay, that's important because a lot of people think, oh, well, you can get a 1. So a lot of people think this. You can roll a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, an 11, and a 12. Right? That's correct. I could. If the sample space, that would be the sample space for the sum. So if they asked you the sum, what is the sample space? So if they said this, sample space for the sum of 2 die or 2 dice, What is the sample space for the sum of two dice? Can't even read that. What is the sample space for the sum of two dice? Well, what are the things that could happen if I add the two die? What are the things that could happen? If I roll two die and I add all the dots, what is the list of things that could happen?
You'll get a number.
So what is the sample space? All the possibilities. So tell me all the possibilities. All the possibilities. Tell me all of the possibilities. Tell me all the possibilities. That's not a sum. What's a sum? I could get a sum of 2. Could get a sum of 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. That's the list. Sample space is a list, either visually or a list like that. Tell me everything that could possibly happen. Okay? Grades in this class. There's only so many grades you can get in this class, right? There's 5 grades. You can't get a Q. There's no such thing as a Q, right? You can't get some grades. Some grades you can't get. There's a sample space of 5, A, B, C, D, F. That's the only things that could happen, right? If you're a student. If you're a TA, it's different. If it's your TA, there's only 2 options, P or NP, pass or no pass, right? Because you don't get grades for TA blocks. You got to ask the teacher. But that is an option. You have 2 options. We always have 2 options, right? Okay. So that's what a sample space is, a list of all possibilities. So actually list the possibilities, okay? Okay, the next one is a probability model. Probability model is a table. Looks like this. On one side, you have the sample space. On the other side, you have the probabilities. On the other side, you have the probabilities. So over here, you're going to have every single thing that could happen. And then over here, you're going to have the probability of those things happening. So if there's a lot of things happening, you're going to have a lot of numbers over here. If there's only, and then for every thing that could happen, you have to have a probability goes with it. That's a probability model. It's a fancy word for a table. Okay? An event is something that happens. Events are usually denoted by capital letters. So sometimes we use A, B, and C. The probability of A, the probability of B, the probability of C. It's something that happens, any event that happens, right? So in other words, if I say the probability, what's the probability that if I roll 2 die, the sum is going to be 6? That's an event. The sum is 6. Okay? Those are just words, vocabulary that go with it. Okay? All right, so here we go. Example number 1. There's a website where humans can play paper, rock, scissors, or rock, paper, scissors. Paper, scissors, rock. I've never heard it like that. It's rock, paper, scissors with a computer. Irresistibly drawn to it, you play the game twice. Assume that the computer is randomly choosing its moves for both games. So right now what I want you to do is give me what are the things that could happen. Wait 1 second. Draw a table. So first thing we're going to do is draw a table. Okay. So we play it 2 times. We play the game 2 times, right? You play the game 2 times. What are the things that could happen? I could win. Okay, so wait, let me word this a little differently. What are the things that can happen if you were to play rock, paper, scissors? So let's play once. What are the things that could happen? If you were to play once, what are the events that could happen? Okay, so some of you guys are talking about rock, paper, scissors, and some of you talking about win or losing. Those are different events. Okay, so let's talk about the actual game. If I play once, what could happen?
You can draw rock or paper.
I could have three options, right? I can have a rock, I can have a papers, or I can have scissors, right? And if I play again, I can have the three options, right? So I'm not playing once. If I was playing once, I would have a P, R, S. But I'm playing twice. So tell me what are the things that could happen if I play twice? Okay, so let's write those down. So I can have a rock. Let me see, actually, I'm probably going to lose. So I can have a paper, a rock, scissors. Are those the only things I could choose?
No, you can have a paper rock.
I could have a paper rock. I'm running out of room here, so let me move these around. Another way to do a table is do it sideways, and I think that's probably the best way to do it this one. So we said paper. We said rock. We said scissors. What else could happen? Paper, rock. What else? Paper, scissors. Scissors, rock. Keep going. Rock, paper. Rock, scissors. Scissors, paper. Scissors, paper. I can do paper. I can do rock. I can do scissors, paper, rock, scissors, paper, scissors, rock, paper, scissors, and scissors, paper. Those are the things that could happen. Those are the only things that could happen. Am I missing one? Okay. Now the probability. What's the probability that I do paper? Or the probability that, let's see, assume the probability that the computer does. Sorry. Obviously I wouldn't do probability of me because I control that. It's not a random event, but I can't control what they're doing. So what's the probability that the computer chooses paper first and then paper second? So how do we get to that probability? That's more my concern. I'm not concerned about the answer. I'm concerned about how we get there.
Because there are 9 possible answers and he has to choose one.
There you go. There are 9 possible things that can happen. Paper, there's only one of them. So it'd be 1/9, right? There's a 1/9 chance that the computer chooses paper. There's a 1/9 chance, a 1/9 chance, a 1/9 chance for everything because it's one event. Right?
Wait, so playing game 2 times are considered one event?
Because they said that's what they said. They said play the game 2 times, so that's my event. It's considered one event. Okay? So event A, define event A as the computer chooses the same move for both. So event A is the same thing as saying the computer chooses the same move for both games. What's the probability of that happening? Well, how many different things can happen? So don't give me answers because answers don't help. Give me ways that we can figure this out. So what are the total possible things that could happen for event A? No, that's not the total possible things that could happen. What's the total possible things that could happen for event A?
He can choose paper both games.
Okay, so you guys are, so remember, the top is what I'm looking for. What I'm looking for is in purple there. The bottom is the total, right? So you guys are telling me the top. I want the bottom. The purple. What does the purple say? So how many different ways can I do the purple? 3. I can do paper, paper, or the computer can. The computer can do paper, paper, rock, rock, scissors, scissors, right? Those are the 3 they can do. That would be considered the same move twice. What's the bottom? 3 out of what?
9.
There you go. That's what I was looking for. There's only 9 things that could happen. Didn't we just list them all out? There's 9 things that could happen. So we reduce that. And we say there's a 1/3 chance. There's a 1/3 chance that the computer picks the same move twice. Okay? Because probability is always, the top is what I'm looking for over the total number of things that can happen. The bottom is always going to be the sample space. The sample space is always goes on the bottom. Everything that could possibly happen. Okay? All right, so now on the back page, the back page is probably the most important page in this whole chapter because it gives you all of the rules and it gives you how to solve all of these problems. Okay? So I have a lot of people who skip this page or don't even consider this page. To me, this is the most important page of this entire chapter because this is where you're going to keep going back to. You're going to keep going back to this page more than any other page because it tells you the rules. Some of them are pretty obvious, like some of them are just common sense. Like the first one, for any event, the probability is either going to be between 0 and 1. Like you can't have over 100% chance that something's going to happen. There can't be a 105% chance that it's going to rain today. There can't be a negative 15% chance that it's going to rain today. Just can't happen, right? You guys already know that. That's common sense, right? That's what the first one says, the first dot. The second dot says, if S is the sample space, the probability of the sample space is 1 whole. So that's like saying, here's the sample space. What's the probability of one of those things happening? 100%. It has to, right? If it's not 100%, it's not the sample space. You're missing something, right? So if I wanted to say that, what is the probability that I roll 2 die and one of those things happens?
100%.
Or else I haven't listed everything, right? Then if I haven't listed everything, it's not the sample space. Okay, that's all that says. Okay. Number 3 is the one you guys all know. The probability of anything is the number of outcomes corresponding to A, so the number of things that happen the way they want them to, right? Doubles. We want it, like we said, the last one was doubles over the total number of things that can happen in the sample space, right? That's the definition of probability. Okay? If I flip a coin, there's 2 things that could happen, heads and tails, right? If I want to know the probability of tails, that's 1 out of 2. That's what you guys told me the other day, which is true, right? True. The theoretical probability of flipping a coin and getting heads is 1/2. Okay? The reason I say theoretical is because it's not actually 1/2. Because if you give me a coin and I flip it 10 times, the chances I get 5 heads and 5 tails, that's not very high. Okay? Okay, the complement rule. Complement just means everything other than that. So if you see that little C, sometimes they don't use a C, sometimes they use a little tick mark. That means everything else. So if I say, for example, go back to this question here. If I say something like this, the probability of scissors and rock, C. What I'm looking for is everything else other than scissors and rock. So what would be the probability or the complement of scissors and rock? 8/9. Everything else that can happen, right? So you could do 1 minus the probability of scissors and rock, or you can just look at everything else. That's the complement rule. They use the word complement Okay, they don't use everything else. They'll say, you'll see that little C there. Okay. Mutually exclusive. Mutually exclusive is one of those big boy words, big boy phrases. Mutually exclusive. It means two things that can't happen at the same time. Two things that cannot happen at the same time. Okay. So what I mean is, let's say the probability of you guys having English class during first period, and the probability of you guys having history class the first period, right? You can only be in one place at the same time, right? So you have one probability for one probability for the other. You can't do both. You can't, if both can't happen, they're called mutually exclusive. Okay, there's not a third option. So if they're mutually exclusive, how do we find their probabilities? We take the probability of A and add it with B. Just add them together. Okay, if they're mutually exclusive.
Wait, by mutually exclusive, do you mean if they're the same?
If no, if they can't happen at the same time. If they can't, two things that can't happen at the same time. I can't be a junior and a senior at the same time. Can't happen. I'm either a junior or I'm a senior. Well, some people think some seniors think some seniors think they're seniors, but they're really juniors because of credits. Your year doesn't count. That's something people don't understand. You'll learn in college, but even though it's your fourth year at this school, it doesn't mean you're a senior. You have to get the credits to be a senior, right? So there's some people on campus who are fourth year, but they have sophomore credits. Yeah. So I'm a senior. Well, no, you're not. Okay. So they're actually not seniors. Okay. So yeah, that's what that means. You learn that in college because there's some people in college who have been there for 5, 6, 7 years and they have sophomore credits. Okay. Except in college, you have to pay for it. So you got to be careful with that. Okay. Multiplication rule for independent events. So independent events are events that have nothing to do with each other. They have no what's the best way to say independent events are two events that have no bearing on each other. Okay, don't affect the probability of each other, right? They're two different things. Yeah, we'll talk more about this later this week, maybe next week. Okay, don't really worry about independent events right now. Okay, but that's what they are. Okay, we'll come back to that one in 5.3. The two that you have, these two guys right here, the two dots, general and general, that's the ones you have on your sheet. Those are the two you have on your sheet, and those are the two we're going to use the most often. These are the two formulas we use the most often in this chapter. That's why they're on your sheet. All right. The general multiplication rule is conditional probability. We'll talk about that next section. Don't worry about this section. This section is more general addition rules. Okay. So if you're looking for the probability of A or B, so these symbols, you see some of these symbols, these U symbols, and these upside down U symbols, kind of looks like a frown. They either mean and or. Okay. So this symbol here is or. This symbol here is and. One is called a union and one is called a intersection. Or means that could happen or that could happen. Either one is okay. And means they both have to happen. They both have to happen. Intersection, right? So if you have two events, or means this one could happen or this one could happen. Okay, it's both, either are okay. And means both have to happen for it to work. That's the difference. Okay? So with the multiplication ones, you see a lot of and. With the addition ones, you see a lot of ors. Okay? We're going to use those formulas all chapter long. So here we go. Independent events. The outcome of one event does not affect the outcome of the other. An example of two independent events. One event is it going to rain today? An independent event with that would be, how am I going to do on the test? Is it going to rain today? How am I going to do on the test? Right? Does it matter? Does the weather have any bearing on how I'm going to do on a test? No, right? No. You studying has everything to do with how I'm going to do on a test, right? So we would say weather and performance on the test are independent of each other because they have nothing to do with each other. It could be raining and I could do well. It could be clear, like today, I could do well, right? They have no bearing on each other. If two things have no bearing on each other, then they are independent events. Okay? No, they're different. And I'll explain why. Yeah, that's a good question. Are they the same thing? No, they're not. They're actually different. Okay? Yeah, so dependent. The opposite of independent is dependent. Dependent would be, I study for a test, my grade on the test. Those are directly tied. Those are directly tied. If I study for a test, the chances I do well on the test go way up. That's research-based, right? That's why we study. Okay? So those are dependent events. Okay, so mutually exclusive. Two events that do not have any outcomes in common, or two events that cannot both happen at the same time.
The events are the events that can never happen.
They cannot both happen. They can't both happen. So like I told you, an event would be class you have during first period. I can't have an elective and an English class at the same time, right? You can only have one or the other. They can't both be your first period, right? There is no English class that's an elective, right? Because English is, you need 4 years of English, right? Math classes, this class is an elective. You don't need to take this class, but you chose to take it for different reasons, right? You only need 3 years of math, right? You need 2 years of science, but you need 4 years of English. So you have to take an English class. Now that there's choices, right? You can take different choices, but you have to take it, right? So there's no way for me to have an elective and English class at the same time. Those two events are mutually exclusive. They can't happen at the same time. Okay? They can't happen at the same time. That's what mutually exclusive means. Two things that don't have any outcomes in common or don't cannot happen at the same time. Okay? So how do I do these problems? There's 4 ways to do these problems. This is what you're going to come to more often than anything. Because you're going to be running into problems and you're going to be like, it looks so simple, but I can't understand how to do it, right? Probability problems are great because they sound so simple. What is the probability? I reach into a bag and I pull out a blue marble, right? They sound so simple, but they're extremely difficult sometimes because you have to mentally picture it. So there's 4 ways that I put here that help students in the past. One is make a table, 2-way table. We're going to do that later, maybe today, maybe tomorrow. Venn diagrams. You've all seen the Venn diagrams, right? 2 circles, they share a piece in the middle. Sometimes 3 circles, right? Tree diagrams. Tree diagrams. Oh, 1 second. Okay.
I love the fact that this time of the day you are teaching passion. You guys know how fortunate you are to have Mr. Flores.
Oh yeah, they all. The last one is using these formulas. Using these formulas here. More than likely, it's going to be one of these guys. One of these guys. Okay? More than likely, it's going to be one of these guys. That's the formula you're going to use. Okay? All right, so let's look at this question right here. Example number 2. Example number 2. Okay. Buffalo Wild Wings, ran a promotion called Blazing Bonus, in which every $25 gift card purchased also gets a bonus gift card for either $5, $15, $25, or $100. Okay? According to the company, here are the probabilities for each bonus gift card. Okay? So what's the probability? So you go in and you buy a $25 gift card for somebody. And then as a bonus, they also throw on top of that either $5, $15, $25, or $100. Okay. Somehow they randomly give you, like, they're like, oh, not only do you get a 25, but you get 5 or 15 or 25 or 100. Okay. So if I were to walk in during this promotion and I were to buy a $25 gift card for someone, there's about an 89% chance that they'd also throw another $5 on top of that. There's about a 10% chance that I'd get a 15. There's about a 1% chance that I'd get 25. And there's even less than that chance that I would get $100 on top of it. Okay. Okay, so explain, is this a valid probability model? In other words, are those all of the things that could happen? Is that the sample space in the box?
Yes.
How do I prove that?
It says we receive bonus gift card for 5, 15, 25, and 100.
Mhm.
Those are the only they can receive.
Right? If it's the sample space, the probability has to be 1. That's the way to prove it. That's the way to prove it. Okay? Because if it doesn't equal 1, that means they left something out. Or if it goes over 1, that means something wrong because it violates the first one and the second one. Okay? So you're going to add up all of the decimals, and do they equal 1 whole or 100%? Good.
Yeah.
Okay. All probabilities equal 1.0 or 1 whole. Here's a 1. Sometimes you'll have a table and you add them all up and you get 0.999 or 1.0001. What do I do then? What if I were to add up all the probabilities and I would get one of those two guys? Is that valid or is there something wrong with it? So let's say I re-go over it. Let's say I re-add them up and I still get those numbers.
But it wouldn't be valid because it specifically said the probability has to equal to 1.
Here's why that'll happen. Here's why it'll happen. And it happens a lot with students because students like to round. Like I have students like this all the time. So if I have a probability of 3, 3, 3, 3, 3, 3 like that, this is what they'll do. Oh yeah, that's 0.3. What's wrong with that when I add them all up? I have students like that all the time. It gets better as it goes up. Like for my Math 1 students, I would have them say, oh, that's 0.3. Math 2 students, they might say, oh, 0.33. Math 3 students might say, oh, well, I'll put a 3 over that, put a little line over that. But I have a lot of students that just say, oh, this is the same thing as, I'll just write 0.3 down. How does that affect my numbers when I all add them? It's not the same, right? Very close, right? It's very close. So exactly. So do I have to write down all of the 3s? No, that's why we write. That's why we do this, right? We write that, right? Even if you were to do that though, and I were to add up the probabilities, I might get something like that. Okay? It's a rounding error. It's called a rounding error. It's okay. It happens. Okay? So first thing, see how they went 3 decimals past? Always do that. That's the first thing. Always go 3 decimals past if you can. And if you get something like this, it's okay. It's just a rounding error. It doesn't mean the table is bad or it doesn't mean the table is wrong. It's just a rounding error. Okay?
Those numbers are valid.
So if you were to get something like this, it does not mean that your table is bad. It means that one of these guys was rounded not the best method. Well, again, so like let's say you get 0.998 or 0.997 or 1.001 or something like that. What I would do is I would look at any of those probabilities. Most of the time it's because you created, most of the time, today is the only time you're really going to see something where they give you the table. Most of the time you're going to create your own table. So what you do if you create your own table is say, well, which ones did I round? That guy around, that guy rounded, that guy rounded. Okay, so that's okay. So you're going to kind of grade your own work. Okay. But just be wary that sometimes you won't get something that equals one whole. It's because of rounding. If it's very, very close, then it's okay. If I get them all, if I add them all up and it's 0.95, that's too far off. Right? If it's 0.99 something, if it's 0.99 something or 1.00 something, that's okay. That's okay. Okay, it's called rounding error. Okay, so find the probability that you don't get a $5 bonus card. Don't get it. Which one of the rules talks about that one? Which one of our rules talks about that situation? That's the complement, right? So what they're saying is the probability that you don't get a 5. That's how they would write it. Probability you don't get a 5. Right? Which is the same thing as 1 minus the probability of getting a $5. Right? You're just adding everything up that's not 5. So when you do that, you get 0.110. Okay. If they use the word probability, keep it as a decimal. Okay. Probability. I had my statistics teacher in college. This drew him nuts. I don't get it, but it's the way they want it. If they use the word probability, keep it as a decimal like that. Don't change it to a percent. No percents. If they say what percent chance, then you can change it to a percent. Okay. But if it has a probability, the word probability in it, keep it as a decimal. They always like it as decimals or fractions. Fractions are okay too. Okay. Here we go now. What is the probability you get a 25 or 100? No, this one's not a complement rule. This is the key word right here. Or. If you see or, automatically, you're going to go back up to the ones you saw or at. Right here, addition rule. Addition rule. Okay? So in other words, we're saying the probability of one event or another event. Either one's okay. So we're going to take the probability of one event. So we're talking about the probability of $25 or $100. So what I'm going to do is I'm going to find the probability of $25. I'm going to add that with the probability of $100, and I'm going to subtract the probability of both happening. And because that's what the formula said. The formula said that. It's on your paper. It's on your neon paper. It said the probability of one plus the probability of the other, and then you're minusing both, the probability of both. Okay? So let's do this. What is the probability of $25? 0.010, right? What's the probability of 100? Okay. And then I'm going to subtract that from the probability of this guy. What's the probability of getting a $25 gift card and a $100 gift card? So this is what has to happen. I have to walk into Buffalo Wild Wings and buy a $25 gift card. And what they have to do for this to be true, what they have to do is give you $25 more and then $100 on top of that. What's the probability of that happening? It's not going to happen, right? They're either going to give me a $5, a $15, a $25, or $100. They're not going to give me 2, right? So the probability of that happening is just 0. So I add straight across, a little over 1%. Write it, keep it as a decimal. So if this guy is 0, last thing we're going to do, last thing, because this is important. If this guy is 0, we call it mutually exclusive. They can't happen at the same time. This guy right here can't happen at the same time. If that's true, it's mutually exclusive. That's how you know if it's mutually exclusive. If they both can't happen, if that guy is 0, like this guy is, getting a $25 extra with a $100 extra can't happen. They're not going to do it. So that's why this guy is mutually exclusive. Okay, if that's 0. All right. Okay, we'll pick up from there tomorrow.